Is it going? Yes. All right. I feel ridiculous. Okay. I want you to know, like, this is how I record all of them. Usually I'm by myself and no one's watching me. Okay, so I know. We are going to just review a little bit. I want you guys to jot down the equation that's actually for the next slide. So it is 2 moles of dinitrogen pentaoxide, and that is going to go into 4 moles of nitrogen dioxide plus oxygen. Okay, if you take a look at that equation, first of all, what kind of equation is it? Dylan? Decomposition. Good. It's a decomposition reaction. So what you heard from the last podcast and what I asked, which compound is going to be decreasing over time? The reactant, so N2O5. And then the products are going to be increasing. So our reaction rate and what did we show that things are decreasing? What sign did we use? Did I say on the podcast? Negative. Okay, so it's going to be a negative change. And the brackets mean what again? Molarity. Okay, so the concentration over our change in time. So we also talked about that this is also going to be equal to, if I use my rate law, is going to be equal to some constant times the concentration raised to some power. Okay? So this is what we need to figure out today. Today we're going to learn how to figure out what K is. We're going to figure out what this exponent is. And remember that we can't just look at the balanced equation. Okay, they're all staring at me, you guys, because I have headphones on in front of class. All right. These kids that are listening to this. Okay, so who sacrifices I make for them, aren't I, you guys? Right? Right? Okay, so we're going to try to figure out K today, and we're going to figure out what this rate is. We're going to figure out units and how it changes all the time. Now, I'm not sure if I said in the podcast, but this can only be done experimentally. Now, I know in the problem of the day, we took a look at this, but was it identified as the slow mechanism? If the equation is written as the slow mechanism, and you know that it is the slow equation, then I can say that that would be a 2. But I can't just say that because I don't have the experimental data with it. So if we take a look at some experimental data, so here's our plot. So we have a plot of the concentration of the equation that you just wrote as a function of time for this reaction. Now you can see, is the rate changing? Okay, the rate is changing. So we have to decide, do I have a 0-order reaction, a first-order reaction, or a second-order reaction? And that's what we're going to try to figure out. And that's the lab that we're going to do on Wednesday. So this reaction rate, though, this rate that you guys are looking at, what factors are determined? What does this depend upon, this rate? Time, okay? Time in terms of what other factors, though, in the equation? So one is the size. So the size of the molecules depend upon this rate of how fast it's going to go. What else? Temperature. Good. What else? Surface area. Good. The energy that's involved in the system. The bond strength. We've been talking a lot about bond strength. We can't forget all of that, you guys. The bond strength meaning, do I have ionic bonding? Do I have LDF? Do I have hydrogen bonding? Do I have dipole? All of those things are in bond strength. And then the last one is orientation of the collisions. Now, in that podcast that you guys saw from Bozeman, he had that good little, was she able to get that one to go? That little diagram of the red and the blue particles, right, and how they orientated themselves, that in order for this to happen, not 100% of all the molecules are always going to collide in the right way to make your product. They have to be orientated in the right way. Obviously, increasing the temperature, increasing surface area is going to help this orientation and the collisions to happen. Okay, so let's start digging in mathematically. I have a lot, you guys, written in here. So write kind of small, start way over here, as you can see on my notes. Okay, so because you can't extend your page like I can, so write small, all right? Okay, so we are going to do example. It's the example on page 534 if you want to go back and look at that. But what they did is the same thing, the reaction that we just wrote. And experiment number 1, they were taking the reactant concentration of N2O5, and they wrote down what the rate of that is, and that was in molarity per second. So capital M, molarity per second. They did 2 experiments, and in the first experiment, the concentration of this was 0.9. The concentration of this was 0.5, so you can see they reduced it by half. And then they measured the rate, which you can see it's the same numbers that were on the graph that you just saw. Okay, so now what we're trying to do, you guys, we're trying to figure out if it's a 0 order, first, or second order reaction. And all that means is the speed in terms of how it's going to go. So what you want to do is you want to compare the experiments one to the other. So if I take experiment 1/2, okay? So if I take experiment 1/2, would you agree that 0.45 goes into 0.90 2 times? Okay, we are going to call this reactant X. So that goes in there 2 to the X times. If I say 2.7 times 10 to the 4th divided into 5.4 times 10 to the negative 4th, that also goes in there 2 times. So what does X equal? 1. Okay, so this is telling you that this is a first order reaction. This will all make more sense once I show you and lay them all out for you. Okay, so what that is saying is that exponent is going to be raised to the first power. So we wrote down that our rate is equal to the decrease, the change in our reactant over our change in time. We said that it has to be done experimentally. So our rate law is going to be our constant K times the concentration raised to the X power. So that's what our rate law is going to be. So we just determined that our rate is going to be K times the concentration to the first power. So what does this all mean? So this is our rate law. All right, so graphically, we first found out what this was experimentally. Remember that you cannot do this unless you do it experimentally. And you can see that in the balanced equation, what was this coefficient right here that you thought may have gone right there? In the balanced equation, what was the coefficient? 2. And you can see that it actually is a first order law. So that's why we had to do it experimentally. So what does this look like graphically? Okay, so I think you guys can squeeze this in over there. So go ahead and write that in over there. I'm actually going to erase and move over there. Okay, so if I take a look, I can say that if I have an XY graph, and I'm going to put my concentration of A over time, and if I plot it and I get a graph like that, this means that my rate is equal to K. So whatever the rate is progressing, that constant is always going to be the same, and this is going to be a 0 order reaction. Well, if I were to take your rate law that I just did and put a 0 in there, anything raised to the 0 power is always what? 1. So is this decreasing by a constant rate? Okay, the concentration's decreasing over time at a constant rate. That's a 0 order. Now, if I were to graph this in terms of rate over time, what would I get? I'd get a straight line, right? So experimentally, if I am doing this back in lab and my concentration is decreasing by a certain rate, then I know that I have zero order because it's constant. Okay? Now we had a first order. So right underneath, let's do first order. You guys squeezing that all in there? Okay, so the second one is we are going to take our concentration over time again. And if I have a first order reaction, it's going to like this. Okay? Yes. And then make sure all the other jets are off. Okay, so this is going to be a first order, you guys. And in a first order, we have our rate is going to be equal to our constant K times the concentration. And this is radioactive decay. What do you guys know about how does radioactive decay decompose? Half-lives, okay? And so if I take a look at this, and if I could say like half of this is decaying, and then half of that is decaying, I know I'm not drawing this very well, but if it is truly a half-life, should these times be equal? Yes, that's a half-life. So radioactive decay is a very good example of a first-order reaction. Radioactive decay. Okay? Now, if I go ahead and take a look at my rate versus time again, like I was doing, it's going to have a nice, this should be straight, it's going to have a nice decreasing line. The other thing, though, that probably will give you more idea of what's actually going on is if I do this over time again, and I take the natural log of my concentration. If I do that, then I'm going to get a straight line. Now, remember we talked about that we have to do this experimentally. So you can get your experimental values, you can plot them, and if I get something that looks like this, my rate over time is straight, then I know I have a zero order. If I take the natural log of my concentrations over time, because I can do that in lab, right, see what my concentrations are, and get a straight line, then I know I have a first order reaction, and it's going to decay in half-lives. We're all talking about the rate of decay. All right, then if I have a second order reaction, concentration of A again over time, and if I have a second order reaction, it's going to look a lot like the first one or this first order reactant, but it's going to be like this. So if I take a look at my first order, and this is my second order right here, what would you say is the difference between these two lines? Which one's faster? The second order, okay? The curve is much less, it decreases quickly, and over time it changes. So this is a second order reaction. Now, those of you that are in calculus, if I were to graph that and find the slope, which is what I'm doing, I could do that. But they, in the AP exam, need to stay away from calc. So what you need to do to figure out if you have a straight line or not, and it will work pretty close where you have a straight line, you take 1 over the concentration of A over time, and if I have a straight line there, then I have a second order reaction. So you should be able to take any experimental data that you have, graph it, and you will be able to tell if you have zero order, first order, or second order reaction. Okay? Now in all of these situations, can I change that rate? Yes, by changing the size, the orientation, the temperature, right? All of those things, I can change these rates. But bare bones, you need to see that if I take that data, that it gave you the first time, we said it was a first order reaction, and I were to graph it, I would get either one of these, depending upon what variables I'm graphing. Okay? Now in all of these, they are going to give you data. So let's look at the next one. So here's initial rates from 3 experiments for the reaction. Here's our equation. you can see that it's 1 to 1 to 1 to 2 moles of water. You can see that they have the initial concentrations of each of these and then its rate. So what I would do right away is I would go ahead and I would label them what you are going to do in your rate law. So I would say that my rate law is equal to some constant K times each of the reactants concentrations raised to some power, I don't know what it is, okay? So I need to figure out what X and Y are. So I am labeling NH4 as X, so I'm going to put that up here. Oh wait, look at that, NH2 and NO2. I was copying that up there. There's a typo there in that graph. Okay, and I'm labeling this one as Y. So we need to figure out X and Y. So what you want to do is we are always going to do, and this is what we're going to do in lab 2, is we're going to hold one variable constant so that we can study the other one. So if I want to figure out what X is, okay, if I want to figure out what X is, do you see how this is held constant and this is held constant, right? So if I want to figure out what X is, which experiments am I going to focus on? 2 and 3. I'm going to figure out what 2 and 3 is, right? Because this is held constant, this is changing, so I can figure out what NH4 is. So if I take a look at the numbers, does it make sense I'm going to go 3 divided by 2 just because the numbers are nicer that way? It doesn't matter which way you do it, the numbers are the same. It's just you don't have to use your calculator then. So I'm going to say experiment 3 over 2. And when I say experiment 3, I have 0.2 divided by 0.1 goes in there how many times? 0.1 goes into 0.2 2 times. I'm figuring out what X is. And then I'm going to go over here to my rate, and I'm going to do the same thing. So I went 0.1 into 0.2. Now I'm going to go 2.7 into 5.4, which is 2 times. So what's X going to be? X equals 1. So is this a first order, just that variable? Just that variable. They don't all have to be the same. It is going to be on this one, but it's not always that way. You'll see that in the next example. Okay, so to figure out Y, which 2 experiments am I going to look at for Y? 1 and 2, because this is held constant, so I can look over here. So I'm going to say experiment, which way am I going to divide? 2 divided by 1, right? 2 divided by 1, so 0.005 goes into 0.1 how many times? Twice. I'm figuring out variable Y, and I do the same thing. 2.70 divided by 1.35 is 2, so Y equals 1. So now I can go ahead and write my rate law expression. This is my rate law expression. So my rate law expression is my rate is equal to some constant K times the concentration of the first reactant raised to the first power. Sometimes you will see the 1 there. Some books will do it with a 1 and some will leave it off. Then you just understood that it's a 1. Okay? Times the concentration of NH2 ion raised to the first power. Now they will also ask you, so this is your rate law expression. They'll also ask you for your overall rate, actually it's reaction, overall reaction order. So this would be, in this case, X plus Y, so ours is equal to 2. So 1 plus 1 is equal to 2, so our overall reaction order is a 2. So they might ask you for your rate law expression, your overall reaction order, and the third thing they'll ask you to find is the value for K. Okay? So you need to calculate K. So to calculate K, it doesn't matter which experiment you use. It doesn't matter. Just grab one. Because the numbers are going to be the same. Now that you have your rate law, you can substitute everything in. The hardest thing about finding K is you have to make sure that you pay attention to the units. The units for K will change for every different order that you have. So if I take a look at experiment 1, because that's the one I think I have worked out, I took experiment 1. So here's my rate, 1.35 times 10 to the negative 7th. That's moles per liter second. And then I would put in my concentrations. Remember, that's molarity for experiment 1. Raise it to the power, calculate K. Okay, so I'll put that all in. So I took experiment 1. So my rate is 1.35 times 10 to the negative 7th moles liter second is equal to K. The concentration of the first reactant was 0.1 raised to the first power. Second, raised to the first power again. So I go through and I calculate K is equal to 2.7 times 10 to the negative 4th. Okay, so mathematically I think that makes sense. Now we have to figure out the units. This is the part that you have to pay attention to your algebra. All right, so this right here, this concentration of this one means molarity, right? What does molarity equal? Okay, so this is moles over liters, and would you agree that that's squared? Okay, so this is squared, and this is K, and on this side we have moles liter second. So I'm solving for K, so am I actually multiplying by the reciprocal of this one then? Right? And cancel that all out. So would you agree then that my units are going to be liters over mole second? Can you see that from here? Yep, you flip that over, cancel it all out, you should get this right here. Do you see that or no? Okay, I'll show you. So I have moles, liters second, flip that, liters squared over moles squared. And then that would cancel out. This cancel out there, seconds are still on the bottom. That would cancel that to a 1. Okay? So these problems aren't that hard, you guys. You just have to, it's just step-by-step experimental data. Okay, so I want you guys to take the next problem. And I want you guys to find the rate law, overall reaction rate, and value of K. And you have three reactants here. So I'm just going to write down the value of K so I can take these headphones off for the rest of everybody else, okay? And help you guys through this. So I want you guys to find your rate law. I want you to find the overall reaction order. And then I want you to find value of K. And I'll just give you guys K, because if you find K, you've done everything else right. So here's the answer for K. 8.0 liters cubed over moles cubed per second. So if you get that, you probably did the rest of this correct. Now, tomorrow, those of you that are going on the French thing, or the rest of you that are going to be here, these are the problems that we're going to work on in class. And if you're not going to be here, then you need to be working on these. You guys are going to have a quiz on these on Thursday, which is going to be just what we just did. It's a problem just like this, box, you figure out rate law, overall reaction order, and K. Same thing. So in your book, I don't know the page number, but it's section 12.3. And I want you to work on questions 23, 25, 26, 27, and 30. And like I said, tomorrow if you're in class, we're going to work on these. I'm not going to do any more lecturing. We're going to work on these and then get ready for our lab on Wednesday. So if you are going to be here, you'll have plenty of time too. Okay? All right, I'm signing off. Stop.